Okay, yeah, we can see your screen right now, and I also start the recording. Yeah, the stage is yours.
All right, excellent. Let's start then. Everybody can see my screen, I suppose. So I would like to thank the organizers, especially Gökhan and Soner, for organizing this meeting for all young physicists. And I'm also very happy to be participating in this meeting. Well, my participation is limited to giving this talk because of some executive duties that we are swamped in recently.
I appreciate this, whatever limit it is.
Well, the title of my talk is Chaos in Mesh-Deformed Yang-Mills Matrix Models. So this is some, let's say, it's going to be some related to a recent work that I have been performing together with my students. And the bulk of the talk will be based on a recent paper that I have written together with Kaan Başkan, Onur Oktay, and Cankut Taşçı. Cankut recently went to US to City College. He is now in Manhattan and he's enjoying himself before the classes start there, I guess. And well, it's also, I will also mention some recent work that we did with Kaan and Cankut that will hopefully appear in the archive as soon as possible until after I finish typing the paper. So let's start with an outline. So I'll start with some motivations and background. And I will then tell you about the Yang-Mills matrix model and some basic features or the preliminaries of this Yang-Mills matrix model. And we will then see how we are going to probe the chaotic dynamics emerging from such matrix models with mass deformations. And in the remaining time, I will also very briefly tell you, I will not go into the details of this ABJM model, but I will tell you just how things are both similar in some part to the Yang-Mills matrix model and how they differ from the Yang-Mills matrix model a little bit, especially in terms of the temperature dependence of the Lyapunov exponent, which measures the chaotic dynamics, amount of chaos in a system. So, well, please do interrupt me if you have questions. So I think Gökhan has been teaching some string theory in the past couple of days. So I will start at a point probably quite an orthogonal to the direction in which the string theory was being developed. I will tell you that there are some matrix models. These are called the BFSS and BMN matrix models, which actually hold a reasonably important place in discussions of M theory and string theory since their discovery or since their proposal in late 90s. These are some gauge theories which are supposed to describe non-perturbatively the dynamics of M theory. Well, of course, they are extremely hard to solve and nobody has solved these matrix models as of yet. But there are various ways of obtaining some information and trying to understand the dynamics of these models. I will tell you in terms of some mathematical formula as well, what's meant by these models. But it turns out that these models have chaotic dynamics. So we will see how that emerges. That is already known also from a historical perspective. So I will maybe remark upon a few things later on. But well, in string theory, there are not only strings. There are also B-branes. So D-branes are not, D-branes are some other objects in string theory, right? Which have their own dynamics. They have their own, say Lagrangians and everything that describe their dynamics. Hold on a second. I have to put something to my elbow because I'm kind of bleeding. Okay.
Are you okay?
Yeah, this is fine. This is my skin at the elbow just peeled off after I came back from my vacation, probably due to some sunlight anyway. But anyway, okay. So that's the thing.
Okay.
Well, where were we? Okay, so we said that there are objects which are these D-branes which have their own dynamics, and we are going to be particularly, I'm not going to tell you what D0 branes are, but these matrix models actually describe the dynamics of these D0 branes. These D0 branes are like point-like objects which have their own dynamics in string theory. So when we talk about matrix models, the matrices or the diagonal entries of these matrices describe the locations of these D0 branes in a if it's the BFSS model, which has a flat background, the diagonal entries of these matrices describe the locations of these D0 branes in a 9+1 dimensional space-time, whereas the off-diagonal entries of these matrices describe the strings or the strings stretching between these D0 branes, roughly speaking, and the excitations of these strings. So if you have these coincident D0 branes, meaning that the distance between the D0 branes are shorter than the string length, essentially, then you have some condensed version of this. And this actually describes a string theoretical black hole. And in the large N, that is the large matrix size and low temperature limit, it describes something called the black brane, which is a string theoretical black hole. So the metric of this configuration in the gravity dual is already known. And one can also say that this is the limit in which this lambda effective, this is the effective 't Hooft coupling, is large because the temperature is low, where, well, this has to be lambda t, where lambda t is the 't Hooft coupling, which is G square N, N is the matrix sizes, or the, well, one actually speaks of some SUN gauge theory, and being, so of the matrices of N by N Hermitian matrices. And G square is the Yang-Mills coupling constant here. Well, there are some not very recent, well, when we were writing this paper in 2019, maybe they were more recent, but now 2012, 2015, but still there are various works that indicate that one can just look at or consider the classical dynamics of these matrix models, which corresponds to the large N but high temperature limit. And one can still obtain some important, valuable information regarding the chaotic dynamics. So this is the high temperature limit of the quantum theory, which is well approximated by the classical theory. So there are some further remarks that I will make later on, if time permits, regarding that. So there is one, perhaps very briefly, I can tell you that there is some numerical evidence for fast scrambling conjecture in this regard, coming from classical analysis of this Gurari paper, which is this Gurari, Stanford, and Schenker in 2015, which states that in black holes, the chaotic dynamics sets in faster than any other reasonable physical systems. So, so this must be some, this is a quantum statement essentially, which is motivated by Seçkin and Seçkin based on the work of Kitev and Preskill a couple of years back from 2008. But even in some classical situations, numerical evidence for fast scrambling can be found, as seen in this reference. And well, I have just, the second point I have just told you. So what else?
Seçkin Hocam,
yes.
Before you move on, just for your information, that your talk is the last talk today, also that we have the free discussion time. So you don't really have time problem. You can take it longer if you like. Like there's no other speaker after you.
Oh, okay. So I can.
You can be relaxed and take your time. Yeah, you can take your time because you said like if time permits. Yeah, time can permit, no problem.
Okay, time can permit, and all right.
Okay.
Very well. So again, in this Gurari paper, they have calculated in the BFSS model from classical analysis the largest Lyapunov exponent, and they have determined it to be, given by this number, some 0.29 times. So you see that the temperature, so this formula gives you the temperature dependence of the classical Lyapunov, largest Lyapunov exponent in the BFSS model. So it goes like T to the power 1/4. I have explicitly written the 't Hooft coupling here, but well, both this paper of Gurari and we will work in the, we will rescale all the dimensionful parameters in the model so that we can effectively set the 't Hooft coupling to unity. And this Lyapunov, so the Lyapunov exponent measures, I will tell you about this as well, measures how chaotic the dynamics of a system is, how fast. So so you can consider something like e to the power lambda L times the time. So this e to the power lambda L times time tells you the exponential growth or the exponential divergence of the phase space trajectories of, if you do classical dynamics, for instance. So it is a direct measure of a chaos. And well, there is another work which is performed at about the same time by this Gurari paper, and also Schenker and Stanford. Schenker is, well, yeah, Schenker and Stanford are also co-authors here, in addition to Maldacena. This is the famous MSS bound on quantum chaos, which tells you that the quantum Lyapunov exponent is bounded, parametrically bounded by the temperature. So in all theories which are holographically dual to some gravity theory, that is their conjecture, and that is the proof they give in their paper. So in order to make such a statement, you have to have some theory which has some sort of an holographic dual in gravity. So, and it turns out that there's another paper by Maldacena that this fermionic matrix model, which is called the Sachdev-Kitev model, is actually saturating this Maldacena-Schenker-Stanford bound. This has been demonstrated by a paper by Maldacena and co-authors in 2016. And it is expected to be so for the BFSS model, but there is no complete proof. There is no full proof for this. And for example, you can compare this classical result of Gurari and look at this bound, and one sees that this classical analysis violates the MSS bound at temperatures at this critical, below this critical temperature. So t to the power 1/4 is a plot like this. T is a linear plot, so they intersect somewhere. So below the point they intersect, the classical analysis violates this bound, and above that it actually complies with it. So, so I can, from here, one can say that the classical analysis is in agreement with the quantum result on the temperatures above this 0.015. And I will also comment on this last point later on in conclusions, but there are some recent studies by Buividovich et al. Using real-time techniques, not Euclidean time techniques, to go beyond the classical approximation using some Gaussian density matrix approach. And this pays off. So they can take some quantum corrections into account in a very nice manner using a Gaussian density matrix. And this leads to a decrease in the values of the Lyapunov exponents and predicts a vanishing Lyapunov exponent at finite temperatures, so that this Lyapunov exponent remains below the Maldacena bound at all temperatures. But there is no confirmation whether it saturates it or not, because this is still an approximation to the full quantum theory. What else here? I think this is the last slide on motivations and background. So this is something that I have probably just mentioned just a little bit. So chaos in Yang-Mills theories is not something new. This was known even in 1980s that there's chaotic dynamics emerging from Yang-Mills theories. And people have tried to use this fact in order to prove confinement in 1980s, but that didn't happen. Also, in the case of the BFSS model, there was a work of Irena Arefeva in late 90s. There are some recent works by Japanese groups on small-sized matrix on BMN model with small matrix sizes. So using fuzzy spheres. So our approach to mass deformed matrix model will also involve some fuzzy spheres, as I will tell you in due time. Apart from that, so it will, our approach will not only involve fuzzy 2 spheres, but it will also involve fuzzy 4 spheres for some reasons that I will also remark upon. But in the BMN model, the fuzzy 2 sphere appears to be a vacuum solution, and whereas the fuzzy 4 sphere appears to be a vacuum solution for a 5 matrix model. So it's like a variant of this BFS or a subsector of this BFSS model, which is comprised of only 5 n by n Hermitian matrices. So these are further remarks that I just wanted to list here, because while we are looking at this mass deformed Yang-Mills matrix model, we will introduce an ansatz configuration which will involve these fuzzy spheres and of dimension 2 and 4 with some collective time dependence in order to get some effective Hamiltonians to probe chaotic dynamics. So if you are just hearing for the first time what a fuzzy sphere, don't worry about it. It's just a set of matrices, so which will trace upon. So you don't have to worry. So very well. So if there are no questions, we can go on to discuss this Yang-Mills matrix model and some its preliminaries. So this is the action of the matrix model. So what's going on here? So there are these xi's, x subscript I is defined as follows. I've split it into 3 groups. So a subindex, so there are 9 matrices. All of them are n by n matrices. N is not given to us as of yet. We will take traces of matrices which are of size, say 5 by 5, 6 by 6, and so on. We'll come to that point later on. But so the capital I index runs from 1 to 9, whereas I split the indices and the small a index runs from 1 to 5 only. This small I is 6, 7, and 8. So there, I don't need the triple dots here, 6, 7, and 8. And there's an x9, which at some point we will set equal to 0. That direction will be frozen. That won't be of any concern to us. So these are the matrices. And we like to write down an action in terms of these matrices. And these matrices, the matrix entries, depend on time only. So all the matrix entries can depend on time. So the action involves only integral over time. And furthermore, we have a kinetic term here, which is given by a covariant derivative. That's because this is still a gauge theory. It's called a matrix gauge theory or matrix quantum mechanics. So the idea is that it's like quantum mechanics because there's only time dependence. There's no space here. So space somehow will emerge from these matrices, but it's another story. So where is the definition of the covariant derivative? It's here. So the covariant derivative is defined in this way, and this AT is a gauge field. There's just a single one gauge field in this entire theory, and that is given by this AT. It's an SUN gauge field which transforms under the SUN gauge transformations in this manner. And
can I ask a question regarding to Lagrangian?
Right, sure.
I don't know. I am not sure if you have mentioned earlier. If you did, please ignore the question. Is there any specific? What is the motivation behind the 9 dimension?
So I haven't mentioned that. The motivation behind the 9 dimension is that this is. There are various things to say, but this is somehow related to a type 2A string theory or a superstring theory, which is formulated, consistently formulated in 9 + 1 dimensions. So I need 9 space dimensions and 1 time. But in this theory, you only see time and matrices, but you see 9 matrices. So this 9 matrices will somehow lead to the description of the emergence of the space-time itself. But as I just remarked, that is another story, which we will not go into. But another point that one might make is that this action, if you are familiar with the Yang-Mills theory, in any dimension, which is like trace F mu nu, that's the action of the Yang-Mills theory. So you can start with a Yang-Mills theory in 9 + 1 dimensions and dimensionally reduce it to 0 + 1 dimensions. That is something that one can do by simply declaring that the fields depend on time only and they are independent of the space coordinates. So then apart from these mesh terms, you will get this action. So hope that this is sufficiently satisfactory answer at the moment. If not...
Hocam, can I ask another question?
Yes, please.
in the original derivation of the bound, well, there were no mass terms, and the virial theorem plays an important role, right? As far as I remember.
Yeah, I mean, with the MSS bound, I'm not talking about the MSS bound as of yet. So the MSS paper doesn't even concretely look at the BFSS model. They just make arguments to the very general setting. But there are no, you can say that they are not looking directly at any mass deformed theory whatsoever.
So, well, it is just, I was thinking the motivation for considering these mass terms is related to somehow, maybe how can we deform that bound or... So I was thinking that was the original motivation, but it seems
I thought the motivation was to break the Smith from...
Right.
So far.
So there are various motivations for having mass deformations. Let me mention one, maybe two, I don't know. Well, one of the motivations is that, we already know that BFSS model has some flat directions, which cause some instability. So that can be avoided in the BMN theory, which is already also a mass deformation of the BFSS, which breaks the some global symmetry, which is the SO9 symmetry of that theory, into SO6 times SO3. So that is, so avoiding flat directions or instabilities is one motivation for introducing mass deformations. And that is also, if you look at, say, n equals to 4 super Yang-Mills theory, right? So that's a very nice theory, but the problem with that theory is that it has too much symmetry. So that it cannot be some realistic extension of the standard model or whatever. So people have been then considering mass deformations of such n equals to 4 super Yang-Mills theories as well, in order to come up with somewhat more realistic theories. So that is another motivation for adding mass deformations. One specific motivations here would be to be able to track the chaotic dynamics in these models in a somewhat simplified setting, because once I have mass deformations, I will be able to introduce fuzzy spheres or configurations with collective time dependence involving fuzzy spheres to probe chaotic dynamics. So fuzzy spheres are like then big blobs of matrices which allow you to probe chaotic dynamics in a somewhat simplified manner rather than the full matrix theory itself. So we'll see further.
I also have a question regarding the mass terms.
Regarding what?
The mass terms.
Yeah, please go on, Gün.
Do we have a specific reason for choosing, like from 1 to 5? We group the mass terms into like 2 groups, 1 to 5,
yeah.
Index 1 to 5, and 6 to 8. Like, do we have a specific reason for breaking the SO9 symmetry into SO5 time?
Right.
SO3?
That's because I'd like to introduce both fuzzy 4 sphere and fuzzy 2 sphere into the model. So that is why we are breaking it in this manner. So I will comment on this in a moment.
Okay.
Yeah. So, well, this is the model. So, and in order to, of course, obtain a action functional, we have to trace over these matrices. So we are taking a trace. There is one further thing that we did here is that I have written this action already in the 't Hooft limit. And where we have set lambda 't Hooft to unity. I cannot select. So in the last item here is I have written somehow I cannot select this, but maybe yeah, but it doesn't happen. So if you want to introduce back the 't Hooft coupling, you can perform these scalings of the matrices XA, the time, and the mass terms in the manner that is given in the last line, and that will bring the lambda 't Hooft coupling factor as 1 over lambda into the action. So that is always a possibility, but it is absolutely fine to work with units in which we set lambda 't Hooft to unity. And what else? So the action has SU and gauge symmetry. So that can be shown by making these gauge transformations. You take the gauge field with this gauge transformation, whereas you transform the matrices in the adjoint fashion in this way, and use the cyclicity of the trace, you'll find that this action is gauge invariant. Well, in addition to the gauge symmetry, if you forget about the mass terms, there is a rigid global symmetry, SO9 symmetry of the BFSS model. That is just so you have 9 matrices, X1 to X9. This SO9 symmetry is simply a rigid rotation among those 9 matrices. That is nothing else. But I'm just writing, of course, the bosonic part of the BFSS model because we are going to look at the classical theory. And well, the full BFSS model is a supersymmetric gauge theory. But the classical or the high temperature limit, which is approximated very well by this classical theory with the classical dynamics, doesn't involve the fermions, because the fermions decouple at high temperature limits. That can also be shown. So, well, and the mass terms break this SO9 global symmetry in this fashion. It breaks it to SO5 times SO3 times, 9 copies of Z2. So you can easily see this. So the first mass term is here. So that involves only the first 5 matrices. So you can now only rotate among those first 5 matrices in order to keep the symmetry, and you can rotate among the other 3. And Z2 means that you can take every matrix to minus itself. So for each matrix, so there are 9 copies of that.
Well, isn't the initial global symmetry all 9 rather than SO9?
No. This is SO9, but that is fine, right?
Okay,
so
okay.
Yeah, you can have this subgroup. Very well. So in order to proceed, one can what one can do is to is to fix the gauge. So one can fix the gauge in the following way. One can take the gauge field to be equal to 0. One can use this gauge. What does this mean? This means the following. So there are 2 different types of equations of motion that you can write from this action. Just the equations of motion are obtained by simply evaluating the Euler-Lagrange equations. This is pure, if you know classical mechanics, you can do it. And, but there are 2 types of equations. Because there are 2 types of degrees of freedom. The matrix is Xi, and the matrix single gauge field AT. So in order to set AT equal to 0, you have to first evaluate its equation of motion. And if you evaluate its equation of motion, you will find this, that there is sum over the index I here from 1 to 9, but we will set x9 to 0 anyway. So, we have also set A2 to 0 after evaluating the equation of motion. And also, if you evaluate the equations of motion for the matrices X, you find what I have written in diamonds and spades. For X9, there is no mass deformation term, so the equation of motion looks like this. And whenever an index is repeated, there is an implicit sum over those indices. And this is the equation of motion for the gauge field, as I have just told you. And it is known as the Gauss law constraint. That is because it is just the same way that it comes, as if you are just looking at the equations of motion in quantum or in electrodynamics or quantum electrodynamics. So in the say the Dirac way, let's say briefly. Very well. Now, if you look at the diamonds and spades, the situation is the following. If you say, so forget about x9, we will set x9 equal to 0 anyway. But if you say, for example, set xi, that is x6, 7, and 8 to 0, then all you are left with is this first equation, the diamond, and the capital I only runs from 1 to 5 then. That's because these x6, 7, and 8 are deemed to be 0. Then you can solve this matrix equation by what is known as some matrices, which we will call the fuzzy four spheres. If you take a tachyonic mass, mu1 squared equal to minus 16. So I will denote this solution of these n by n matrices by YA, just very briefly. And these fuzzy four spheres are some matrices which satisfy a symmetry condition, just like a four sphere would satisfy if its isometric group being SO5. So if you consider a four sphere, so let's start with a two sphere. If you have a two sphere, the isometric group of a two sphere is SO3, right? Because you can rotate the sphere. So it's the isometric group is group of rotations SO3. But if you want to consider the spinors and so on, you will consider its double cover, which is the SU2. So if you now increase the dimension of the sphere, so you can go to higher dimensional spheres. Instead of a two-dimensional sphere, you can have a three-dimensional sphere, which we don't have here. But you can have a four-dimensional sphere, which means that now that the isometric group or the group of symmetries for the four sphere would be SO5. So spatial orthogonal matrices, 5 by 5 matrices, right? That will be one representation, defining representation of SO5. So what we have as a fuzzy two sphere is some n by n matrices which carry the representation of SU2 or SO3. So so you can have some n by n matrices which carry the irreducible spin J representation, which is in association with the dimension of these matrices. J will be n minus 1 over 2. And these will be deemed or defined as the fuzzy sphere of spin level J.
Seçkin Hocam, sorry, that will be fuzzy two sphere, right?
That is, that is the fuzzy
It's a typo,
two-sphere.
right?
Right.
Yeah.
No. This is a fuzzy two-sphere. This one, the highlighted
The
thing.
sentence above it, it says fuzzy four-sphere. Isn't it a typo? There should be, just right there.
This is, that must be two-sphere. Yeah, that's a typo.
Okay, good.
Right.
And another question.
Yeah.
So in the case of fuzzy four-spheres, like, why do we get the irreducible representations with 0 and n, like those special cases?
That is because of the construction of the fuzzy four-sphere. So which I haven't went into the description here, but just like in the fuzzy, so this comes from the symmetric tensor product of the 0,1 representations of SO5. So this is an n-fold symmetric tensor product of, the symmetric part of the n-fold tensor product of 0,1, the four-dimensional representation of SO5.
Are these Dinkin labels, 0 and n?
Right. They are the Dinkin labels. But 0,1 represents the four-dimensional representation of SO5, which you
I'm having a hard time in my, like, if it was SO4, there's the chirals, like there's the parity symmetry between the Dinkin indices, like parity exchange names. So I would say they're like the right chiral representation or something like that. But I'm aware it's SO5, so there's no chirality here. So I was having a hard time interpreting what would one of them being
these
0.
are the Dinkin indices. So if there are two, so the defining representations are 0,1, which is the four-dimensional one, and the vector representation is 1,0. That is the five-dimensional one.
Okay, thank you.
Okay. So that is the notation. Yeah, I didn't go into any of these in these slides.
It's fine, but that was helpful. Thank you.
Yeah, that's so this 0,1 representation, the four-dimensional representation, is constructed using the Euclidean gamma matrices. And one can in fact devise a Schwinger construction in terms of oscillators, just like the Schwinger construction for the SU2 generators. And this S0,n is the symmetric tensor product of these four-dimensional spinor representations of SO5, if you like. So, well, the whole setting is then, but there is one funny thing, is that fuzzy two-sphere, so this must be 2, happens to exist at any matrix level. So give me a 2x2 matrix. I call that, so that will be representing a fuzzy two-sphere of spin 1/2. A 3x3 matrix will be describing a fuzzy sphere of spin 1, and so on. Any matrix size is fine. But for the fuzzy four spheres, that's not the case. You can only get matrix approximations to the algebra of functions on the four sphere by these matrix sizes. So you can start with n equals to 1 here. So that gives you, I think then capital N will be equal to 4 then. So you will have n equals to 2, then capital N will be equal to 10, n equals to 3 will give you 20
Is that the
items.
dimension of the representation?
What? That is the dimension of this representation, yes.
Yeah,
Yeah.
Okay.
Yeah, so that is then that this restricts how the matrix sizes. You cannot have any matrix size that you want.
Okay, thanks.
All right, so this is just very extremely briefly how the fuzzy two spheres and fuzzy four spheres are being introduced into this matrix model, because they are actually the solutions of these equations of motion in some limiting cases, as I have just described here.
Jem, can I ask you a quick question?
Yep.
About the last slide, you mentioned that you can't have any matrix size for fuzzy force spheres. Does that somehow affect the Largian limit or similar discussions?
No, it doesn't, because so it in fact is something something useful in a sense that this fuzzy force sphere gets the matrix approximation grows much faster than a fuzzy two sphere. So it's a perk rather than
I see.
Rather than something unwanted. So maybe I should, although Soner said that we have all the time that we could, maybe I should speed up, because I have spent quite a bit of time in these slides. Well, okay, so I will introduce this ansatz. So these RT and YT are just real functions of time, and we will consider XA as some matrices, YA, the fuzzy four-sphere matrices times this RT, and whereas XI are going to be given by some fuzzy two-sphere matrices of the same size, coincident with this N, of course. Otherwise, although fuzzy two spheres exist for any matrix size, once I fix the matrix size, it has to be both the same for the fuzzy two spheres and the fuzzy four spheres, if I want to have a consistent theory, of course. So, and we simply introduce these matrices into the action as an ansatz configuration and trace over these matrices to obtain a family of reduced effective Hamiltonians.
Are there any constraints or conditions on these functions? Like I presume they are like smooth analytic functions, but...
Oh, you mean RT and YT? Yeah, they are just smooth real functions of time, of the parameter T, if you like.
But like, do I need to go to 0 as T goes to infinity or something like that? Or any boundary condition?
Oh, no, we don't impose any boundary conditions. So you'll see, for example, if you look at here, well, of course, one can explore such an Hamiltonian in the, by looking at the R infinity by infinity limit, but you don't have to impose any conditions. It's like a potential like this, for example. I will describe to you what happens there.
Regarding constraints, so I think
you mean this constraint?
Yes. How did we get rid of that? Like
we didn't get rid of. We satisfied it by choosing the configuration.
Okay, the ansatz. Yeah, satisfies it. Okay, we know
the ansatz satisfies the Gauss law constraint. So that is one reason why we have chosen the ansatz the way that we did. There could be other ways to choose the ansatz. I will tell you other stories as we proceed. So, very well. Well, of course, if we simply were taking traces over fuzzy two-sphere matrices, it would have been rather easy to evaluate all the traces analytically and obtain a full analytic answer at any matrix level. But that turns out to be a very difficult task to take traces in a generic representation of SO5, like 0n, this representation I have displayed in the previous slide. So one has to resort to some numerical means, and in particular MATLAB and Mathematica. So, and take small n running from 1 to 6. So this is reasonable enough, because if you run small n from 1 to 6, you get quite a large matrix sizes in terms of the capital N here. And we can evaluate, so Kaan, Cankut, Onur, they have all, in fact, the original probably MATLAB calculations to write down the fuzzy four-sphere matrices was due to Ümit Hasan, Coşkun, who is in Kentucky now, or maybe in California at the moment, but which we have used also in a previous paper. But anyway, so just generate these matrices and obtain their traces numerically. So this is what we get. This is the Hamiltonian that we obtain. So PR and PY are simply the conjugate momenta associated to RT and YT. And this Vn Ry is the effective potential, and the coefficients C1, C2, and C3 are numerically obtained, evaluated, or just by MATLAB. So they differ for different matrix levels. And we have also looked into n equals to 7 case by extrapolating these results for the coefficient C by a rational function to fit the traces of the first 6 cases. So I will display also the results of the n equals to 7 case, which are kind of different. So it might be related to this case as well, this reason as well.
Seçkin Hocam,
yes.
I'm sorry to interrupt again. If we go back to the earlier slide with C1, C2, and etc. Yeah. So these are just positive. Like I'm asking because we start with tachyonic masses in the S1 theory.
Right.
So, but these are not necessarily tachyonic, right? Like C1, C2, they may be positive, I guess.
So the coefficients C1, C2, C3 are positive. So
but that means like this is a real mass.
But mu1 square and mu2 square. So I will show you examples in which either both of them are tachyonic, or one of them is tachyonic, the other one is not.
Here, C1 and C2 is like mass, right? Because it's the Hamiltonian, it's like P square over mass.
So C1, these are just dimensionless coefficients. The masses are here.
But in the formula above, isn't PR and PY are like momenta? I thought they were like momenta.
These are the conjugate momenta of the. Oh, you mean these C1 and?
Yeah, exactly. They should be like mass, right?
Well, you can kind of say that, but I mean they don't have the dimensions of mass at least in the units that we are using.
Okay, then I thought, okay, my bad.
Yeah, see, I mean, if you look at, for example, here, right, it will be like C1 times R to the power 4. So if you take units in which R is like length, C1 won't have units of mass.
Yeah, right. No, I was looking. I was assuming like H is like energy and P is like momenta. So
yeah, P.
But yeah, it's just the conjugate momenta. So
yeah, these are just coefficients in a sense.
Yeah, just okay. Yeah. I see the point now. So
yeah, the mass differ. The explicit they are here.
Okay, yeah, I missed that.
Okay. No,
they carry the same sign with the mass terms, right? Because you have mu squared in the mass terms.
What are you asking, Gökhan?
Well, I mean, of course, I mean, it doesn't have the dimensions of mass, but it carries the same signs with the mass terms, right? So if C1 is negative, then
no. All these coefficients C are conventionally picked to be positive. So the point is the following. So what we do is the following. So you have this action, right? So I substitute these matrices into the action and take traces.
Yeah, but just like Soner, I was thinking when we take the traces, then these numbers, they turn out to be negative too. But you say they don't.
No, they don't. So it is fixed in such a way that that they don't. Yeah. I mean, you can write down explicitly the mesh squares and redefine the coefficients so that some coefficients could look negative, some others could look positive, and so on. But this is just a convenient way of writing stuff. So that's the reason. Any other questions? Hope that this is all right. The point here is that maybe this is just an early remark. There is so you see that regardless of the mass terms being tachyonic or not, these are like harmonic terms. So this effective Hamiltonian looks like just classical mechanics, point particle classical mechanics, essentially, where there are harmonic terms, there are quartic terms, r to the power 4, y to the power 4, and there's a mixed quartic term, r squared, y squared. This last term is responsible for the entire chaotic dynamics. So if the last term is absent, there won't be any chaotic dynamics. So, let's proceed. Well, in order to get some handle on investigating the chaos, we can look at the fixed points of this Hamiltonian. What are fixed points in the phase space? So the fixed points, by definition, are given by setting the time derivative or the t derivative of the phase space coordinates to 0. And one can then solve these equations at given matrix level and find the fixed points. So I have listed the fixed points here for the cases of the matrices n equals to up to 7. And for these tachyonic masses, I have listed also the energies of these at these fixed points. So what we will learn from here is the following. So you see that one of these fixed points has 0 energy, but I told you that C1 and C2 and all C's are positive. So you see that these fixed points have negative energy. And the minimum values for the fixed point, so I have divided by this by n squared. We will discuss why it's being done so just a little later on. But this also has negative values at these fixed points, which are listed in this table. But these energies of these fixed points, as you can see, are and with increasing and at much higher level than the minimum of the potential. So, the potential minimum or value of the potentials are negative in general. That's because of the massive deformation terms, and in particular that's because the masses are tachyonic. So there's one more point before I start to display some results on chaos, and that is the issue of stability around these fixed points. This is also a classical analysis. So one can assess the stability in phase space by looking at the properties of the fixed points in the phase space. So this is just a generic notation to write down the Jacobian matrix in this manner. So these are Ry and their conjugate momenta are simply denoted from G1 to G4. So this is a Jacobian matrix. And the general theory in this setting tells you that the fixed point is stable if all the eigenvalues of J are negative, and if one or more of the eigenvalues of a given fixed point is say positive, then that's an unstable fixed point. And it could be that the eigenvalues are purely imaginary, then this first order analysis is inconclusive. You get a borderline case. So we find that this point where all the phase space variables are equal to 0, and these points, there are 4 such points in the phase space. You can put plus minus in front of each h that you like, but it will be sufficient to just consider one of these. These are unstable fixed points. There are borderline cases, which we don't bother because the numerical analysis doesn't seem to be depending on the stability of these borderline cases at all. They are much weaker in generating chaos and so on, as far as we can tell. And further, since the fixed point energy of this unstable fixed point is 0, the other fixed point energy is negative, so it is less than 0. So then we expect from this analysis that the chaotic dynamics will start to kick in at and around the fixed point energy of these unstable fixed points rather than this one. And that happens to be the case as well. But how am I doing on time, Soner? So I have completed an hour.
Yeah, so if well, we right now we have another hour, like for a full hour discussion time normally.
Yeah.
It depends whether people want to hang out. So I would be happy to keep listening to you. So if you are fine with it, we will be listening. If everyone wants to leave, technically we it's finished. But
okay, let me try to wind up in 15-20 minutes. Then if other loose points are there, we can continue discussing after that.
Okay, that sounds good.
Informal fashion.
Okay, sounds good.
Very well. So this is a crash course on Lyapunov spectrum. So if you, as Sidney Coleman tells in his lectures, if you shuffle through, you will find that if you don't know Lie groups, you won't learn it here, but then he tells you a few things about Lie groups and Lie algebras. So if you don't know about Lyapunov spectrum, you won't learn it completely from this slide, but still you can catch a few things. So one of the basic tools to probe chaos is Lyapunov exponents. So this this measures how the phase space trajectories diverge. So if this x of t simply shows you the phase space coordinates in a chaotic system, the perturbations from this phase space coordinate will deviate exponentially from this initial value at, say, time t equals to t0 or t is 0. So in equations, I can write it in this form. So this is essentially the equivalent to the Coin definition of chaos, namely that if you change the initial conditions just a little bit, you get completely diverging phase space trajectories. So this equation is equivalent to that statement. And what measures the diverging phase space trajectories is this number, which is called the Lyapunov exponent. So there is some technical way of evaluating Lyapunov exponents by some transfer matrix. but normally, of course, there is no analytic calculation of such a messy calculation. Normally, all such calculations are performed unless the system is extremely simple and somehow you can analytically go on to calculate some stuff. This is a way of evaluating Lyapunov exponents. So let me just confine my remarks to Hamiltonian systems. So Lyapunov discussion can be given in a more mathematical oriented way. So a system of differential equations can lead to some definition of Lyapunov exponents. But physics-wise, if you have a Hamiltonian system of, say, some number of phase space variables, which is an even number, right? Then you will have some equal number of, so if you have a 10-dimensional phase space, you will have 10 Lyapunov exponents, 10 different numbers. And well, in addition to that, two of these numbers will be essentially equal to 0, because there won't be any divergence of the trajectory along the original trajectory, which is dictated by the solutions of the equations of motion. So, so two of the Lyapunov exponents will be 0, and the remaining Lyapunov exponents will come in pairs, meaning that if there's a positive Lyapunov exponent, there will be another one which is completely the negative of that. And so that the Lyapunov exponents add up to, if you add all the Lyapunov exponents in a system, they will add up to 0. And this is consistent in view of the Liouville's theorem in classical mechanics also. Well, you can, of course, discuss this also in statistical physics, but namely the volume of the phase space remains the same. This must be small t in time. So that can happen only if the Lyapunov exponents add up to 0. So these are the results of the Lyapunov spectrum. I mean, these are not the important results that I'm showing you. These results tell you that there is chaos. So these results are the confirmation that the system is chaotic, except for n equal, well, I will tell you what happens in the n equals to 1 case. But simply what you see here is just disregard n equals to 1. In all other cases, there is a time series of the Lyapunov exponents are depicted here. So in order to obtain this, you solve the Hamilton's equations of motion at a given matrix level. And then there must be some sort of an algorithm to calculate these Lyapunov exponents. I'm not going into any technical details there. That's quite a bit of technical work. So you see that, for example, n equals to 2, you see that there's this blue curve, which converges to some value just above 0.6. There is this violet or purple, whatever the color is. That is the complete asymmetric of this blue one. So it is the negative value, whereas these two are simply converging to 0 and consistent with these facts that I have just told you. So, but if you want to detect chaos in a system, so this is a system with 4-dimensional phase space. So 2 of the Lyapunov exponents will be 0. Then the other 2 need to add up to 0. And if there is chaos in a system, then there must at least be one positive Lyapunov exponent. And this is the case here. If you have just a single positive Lyapunov exponent, then you can say that conclude that the system is chaotic. So these are the results for different matrix sizes. And for the n equals to 1 level, the matrix sizes are, this is 4 by 4 matrices. So although they are not too small, for the type of models that we look in, you see that if the energy over n squared increases to a larger extent, you lose chaotic dynamics. So n equals to 1 case is a spatial case in which the chaotic dynamics is only restricted to some certain energy intervals. So it's...
So we have like a chaos window.
I'm sorry?
So it's like we have a chaos window.
Right. So there's an energy window in which there is chaos. And once you exceed that energies, there is no further chaos remaining. So these are the Poincare sections for the same situation. For the n equals to 1, so you can see the window in which there's chaotic dynamics, this middle figure. So let me not tell you at the moment what Poincare sections are. If in the discussion section there's some curiosity, I will tell you. But this is just a plot of, so it's the ingenuity of Poincare to describe dynamics in a various fashion. So there's the phase-space trajectory is simply impossible to draw in higher with phase space of 4 or higher dimensions. So Poincare suggested that let's put a plane, and every time the trajectory passes through some certain point and it penetrates that plane, let's put a point there and let's draw the this whole set of points that you accumulate after some time on that plane. So that's the idea of the Poincare section. And if you have a whole sprinkle of points, that means that you have chaos. And if you have these closed curves, instead, that means that you have quasi-periodic orbits. That is the generalization of the periodic orbits to potentials, which has quartic terms and so on. And such closed curves are also called the KAM tori in this context, which also has some very nice theory about those, which I will not go into at the moment. So what we learn from these Poincare sections is that if you, for example, for n equals to 2, the critical, well, these energies are given in the case of Poincare sections by lifting the the energies to, well, we have, in order to draw the Poincare sections for some technical reasons, we have added a constant term to the potential to lift the minimum of the potential to 0. So instead of E, there is an E prime here. But the main idea is that once the energies exceed the energy of the fixed point, you see that the chaotic dynamics starts to develop. So that's the whole point. So let me not lose too much time on this. And let me tell you about, since I'd like to wrap up in a little bit of time, let me tell you about the dependence of the Lyapunov exponents on energy, and then also on temperature, so that we can conclude. So at each matrix level, we can look at how, so instead of looking at, say, time series of Lyapunov exponents, we can run the code again at different energies, find the highest Lyapunov, the largest value of the largest Lyapunov exponent at a given energy. And this is being done by say, running some code with, say, 40, 50 times with different initial conditions in a randomly selected way and averaging these results, so that from those runs and averagings also we get some error bars, which are kind of little in here, but somewhat larger in some other cases. So we can see how the largest Lyapunov exponent changes as a function of E over n squared. So these are the data points, and there are some curves which we have fitted into these plots. So what we learn from here is the following. So look at the plots. For n equals to 7, the situation is not very nice, because it might be that our extrapolation of the coefficients is not very accurate. That might be one of the reasons, which is not absolutely clear, but that's all right. So there are some yellow data points here as well. So there is some technical issue about selecting initial conditions which don't hit on quasi-periodic orbits and so on. Those are, let me not discuss them at the moment. But the main idea is that we would like to look at the fitting curves of this form. And you can ask why the power is 1 over 4, but recall that in the motivations part, I have displayed a formula in which the Lyapunov exponents go with the 1 over 4th power of the temperature. So, and I will show you some, discussion in which the energy will be proportional to the temperature, as we will see. So it is suggestive from such discussions in retrospect that such a functional form for the Lyapunov exponents would be reasonable to check. And here also we have included the fixed point energies, which are all negative. And these incorporate the effects of, in a, if you like, these fixed point energies involve the mass deformation. So they are implicitly depend on the, they explicitly depend on the mass, if you like. But for the time being, I'm using the mass terms, which is -16 and -2 for the fuzzy 4 sphere and the fuzzy 2 sphere. So these are the fitting curves are these, are given accordingly. And the fits are not all right. And also in some other mass situation, they will be better, as I will show you. But let's now see how we can finally relate all this discussion to the temperature dependence of the Lyapunov exponents. So this is the most interesting part of this whole work, to make contact with the existing literature. So what we do, and well, of course, the Gurari paper treats the entire VFSS model in a somewhat more numerically more, let's say, sophisticated fashion. Our model is somewhat numerically less technical than those, but still we can come up with some nice features. So in the BFSS model, there are no mass deformation terms. And then from the virile and the equipartition theorems, so this part is the virile theorem, because, let me just quickly go back here. If you forget about these mass terms, this potential is purely 4th power of the axis. So it's a homogeneous polynomial of the matrix is X, which means of the power 4, which means that the Vireil theorem, just as if you have written a potential like X to the power 4 only, works out completely fine, and you get that the average kinetic energy is twice that of the potential, and this equality is simply the equipartition theorem, and this end of has nothing to do with the small n. This is the number of degrees of freedom which one has to count from the matrix model. And this is not a difficult thing. So you have to take into account the Gauss law constraint and everything. But at large n, in the pure BFSS model, this count is 8n squared. And as I have told you before, so the Gurari paper found this relation based on the dimensional analysis. The lambda L should go like lambda T times temperature times 1 over to the power 1/4, and this is the critical temperature. So we can adapt these considerations, but we have mass deformation terms. So the Vireil theorem won't work as it works here, because the potential is not an homogeneous polynomial. So there are two different identities that I can write. Either these are the clubs, and this is the space. Well, the clubs tells you that the kinetic energy is larger than the potential for Hermitian matrices, whereas the spades tell us for if both of these mass terms are tachyonic, spades tell something stronger, that the kinetic energy is larger than twice the potential. And therefore, instead of the equality, we have this inequality that relates the energy with temperature. And in addition, since X9, we have already set it equal to 0, some degrees of freedom are discarded. And instead of 8n squared, the proper count comes to 7n squared for the original degrees of freedom in the original matrix model. So just insert 7n squared here, then take n squared to divide both sides. So we obtain an inequality which relates the energy and temperature in this form. And now this can be used together with our fitting curve. So the alpha n's are obtained from the curves that we fit to the data. And from here, we can put an upper bound on the temperature above which the MSS bound will be satisfied, and but it is not absolutely immediate that just below this critical temperature that the MSS bound is violated, but it will eventually be violated at some temperature below this upper bound for the temperature. So this is what we have found. So if you like, so you can, instead of E over n squared, insert 21/4 times t here, instead of E over n squared, and then compare this with the MSS bound. So if you look at the equality, you can solve for the critical temperature. That critical temperature is an upper bound on the temperatures above which the MSS bound is safe, but below which it will eventually be violated. So, well, there are also some estimates here for how the MSS bound is satisfied for E much larger than the fixed point energy. So beta n is also given here. It's just some additional number that one can extract from all these discussions. So, but the main point is this middle column. So we can estimate the upper bound for the critical temperature from these matrix models. So the results, as you can see, if you keep on increasing the matrix size, the 't Hooft limit becomes better and better. And then you see a decrease in the upper bound for the critical temperature. But yet still, this upper bound is an order of magnitude larger, essentially, than the 0.015 that is found by this Burari for the pure BFSS model. Well, maybe I should wrap up. So you can, as I have just told you at some point, I can, for example, look at mass values in which one of the masses is tachyonic, the other one is not. And then you won't get the relevant fixed point energy will be the one which gives you the zero energy. So there won't be any term in this fitting curves which is like minus EF there, because that EF value will be zero. And in these cases, still n equals to 1 case is not chaotic. For the other cases, the fitting curves are somewhat better. And also the critical temperatures estimated seems to be somewhat, it's just like twice what is being found for the BFSS case. So one can also do some sort of an analysis on what sort of masses would be most suitable to lower the critical temperature and so on. But that is like an exercise on some further detailed numerical analysis. Very well, let me not go into these. Also, let's not go into these. Well, summary of results. Well, we have studied this chaotic dynamics in Yang-Mills matrix models with mass deformations. So the main result is putting an upper bound on the critical temperatures on the Lyapunov exponent, where above which the Maldacena bound is satisfied, below which it will be violated eventually. Well, there are some comments here which are related to some other ansatz, which I didn't cover in this talk. Maybe I have another. Okay, so there could be some further new developments as some of these papers I have also suggested Günther read some time ago. They are quite clever papers, and there are lots of things to learn from them. So which takes this entire discussion to a quantum level using a Gaussian state approximation. So their methods are inspired from quantum chemistry, in fact, because quantum chemists are desperate to solve some equations involving like n particles. So they have devised some very nice techniques in the past. And well, so the point here is that this is a real-time technique. If you take the BFSS model to Euclidean time, you can impose periodic and anti-periodic boundary conditions on bosons and fermions to look at the phase diagram of this theory, which could be quite appealing to Soner, I guess.
Yes.
So there's a whole bunch of work in that direction, which has already been performed. So people have tried to see there is some ordered phase, disordered phase. There's how the phase transition happens, whether there are, so in some cases, increasing the numerical accuracy has shown that people originally have predicted that there is some sort of second order phase transition followed by a third order one in these matrix models, passing from disordered to ordered phase and so on. But increasing the numerical precision shows in some circumstances that that could only be just a single first order phase transition instead of some successive higher order phase transitions. And there is also some work to understand how, and these guys, Vujvodovich is also discussing that, how this real-time results that they get in terms of understanding the passage from chaos to non-chaos can also be reflected as a phase transition from, so the chaos to non-chaos is a kind of a phase transition that one can discuss also in real time, but also looking at the matrix model in the Euclidean time, you'll see these phase transitions, and there is some, speculations and somewhat more concrete work to see if they somehow overlap. But that is not very, I think one has to still read this paper. Quite
I don't remember seeing anything regarding Euclidean time in that paper.
I think there is some, they are discussing toward the, after the middle of the paper, there are some discussions.
That I probably didn't read it.
Not very early in the paper. But the discussions, I would say, are not very, but there are some discussions. Maybe there are some subsequent papers as well, that they are saying that there is some overlap. Yeah, but one has to look into it somewhat further. Well, anyway, thanks for listening. Hope that it was useful to you. And if you have any questions, let's discuss.
Hocam, thank you so much for this beautiful talk. I also am feeling very happy that I've been talking about phase transitions and phase diagrams for the past 2 days. So yeah, it's nice to see another related concept as well. Does anyone have any questions?
I actually have questions regarding phase diagrams, since we also talked about it today a lot. I mean, I don't recall seeing anything like any phase diagram of, I don't know, BFSS, BMN. Do you know of any just phase diagrams? I'm like chaotic to like integrable transitions. Have anybody just?
No, see, Gün, you know Badis Yidri's book.
Yes, yes.
So the entire phase transition in the BFSS model, phase transition, the whole thing is being discussed in the Euclidean, of course, in the Euclidean time formalism. In those lecture notes and the books. So that's a good review, but they don't, of course, in that regard, they don't discuss chaos at all. They're historically and also technical wise, that discussion is like a discussion of a Lagrangian or an action. It's a statistical model. You switch to Euclidean time. There are periodic boundary conditions on the fermions and the bosons. Antiperiodic on fermions. So, and there are some functions that you can, so you will write down the partition function, evaluate the partition function at, say, either by Monte Carlo means numerically, or just obtain the one loop effective action for the BFSS and BFN models by analytic calculation, which can be done. There are these papers by the Japanese Kawahara et al. From mid-2000s. And there are recent papers by Danjo O'Connor and his collaborators. Essentially, you treat it as a statistical mechanics, statistical physics theory, statistical field theory model, in which you look at some average values of some quantities, like one can define something called the radius, some other functions and so on, to probe and use those average values of those functions to probe phase diagram.
As in statistical mechanics, because
right. It's like once you switch to Euclidean time and write the effective actions and so on, it's like the entire thing is just oriented in that fashion.
But
then there is
Seçkin Hocam, may I say something?
Yes, of course.
Sorry, Gün, you know, I wrote down today like the partition. I compared the partition function and vacuum generating function, like Z.
Yes, yes.
Do you remember they have exactly the same form in the pattern table? It's exactly like what actually we're talking about.
No, I know.
Once you write down Euclidean signature, they are basically the same integrals.
Yeah, but my question is different. Like after weak rotating to obtain the statistical mechanics partition function with like beta and all sorts of stuff. Like we cannot interpret a phase transition as a transition from chaos to non-chaos, right?
No, there is no discussion of chaos.
Right, we can't discuss chaos in that setting.
Now that there is these real-time techniques, one can give some correspondence between the chaos non-chaos transition that people see in the real time, that the disordered phase, ordered phase transitions, or confining, the non-confining phase transition that you see in the Euclidean times formalism.
Okay, that's what you mean by an overlap, right?
Yeah, that's why I mean like a correspondence.
Okay, now I get it.
Yeah.
Thank you.
Yeah.
Are there any other questions? If not, let's thank our speaker again. Thank you so much, Seçkin Hocam. This was a lovely talk.
I thank you for this opportunity.
Okay, I'm stopping the recording then.